Hey everyone, welcome back. Ready to dive into the atom. We've got textbooks, diagrams, even some solved problems, all about how this tiny building block of the universe works.
It's amazing how something so small can be so complex.
It really is. But don't worry, we're going to break it all down so you can, understand it.
Like a detective story, we're following the clues scientists use to figure out what atoms are really like.
Exactly.
Yeah.
So first things first, atoms are like the basic unit of matter.
Yeah. Everything around us, from the air we breathe to, everything is made of atoms.
I know, it's mind-blowing. But how did we even figure out what they look like?
Well, one early model was the plum pudding model.
Plum pudding. Like the dessert?
Yep, kind of. Imagine a sphere of positive charge, kind of like a fluffy cloud.
Okay, I can see that.
And then scattered throughout this are the negative electrons, like raisins in the pudding.
Interesting. But this model, it didn't really explain everything, did it?
It didn't. For example, it couldn't explain the spectral series of hydrogen atoms.
Spectral series. Remind me what that is again.
So each element, when you excite it, it emits light at very specific wavelengths. It's like a fingerprint unique to that element.
Right.
The plum pudding model couldn't explain why those wavelengths were so specific.
So scientists knew they needed a better model.
They did. And that's where the famous gold foil experiment comes in.
The one by Rutherford, right?
Yes. It changed everything. Imagine they fired these tiny particles, alpha particles, at a super thin sheet of gold foil.
How thin are we talking?
Like 2.1 times 10 to the power of -7 meters thin.
Whoa, that's thinner than, I don't even know what.
Way thinner than paper. Anyway, based on the plum pudding model, those particles should have passed through with, maybe a little deflection.
Right, like shooting bullets through a cloud or something.
Exactly, but that's not what happened.
Oh, what happened then?
Well, most did pass through, but some were deflected at huge angles, some even bounced straight back.
What? That's crazy.
I know, it was a total shock. It meant there had to be something small, dense, and positive in the center, something those particles were hitting.
That's how we discovered the nucleus.
It is. Rutherford proposed that the atom was mostly empty space, with a tiny nucleus in the middle.
And the electrons orbited around this nucleus, right?
Yeah, kind of like planets around the sun, but there were still problems with this model.
Before we get into those, let's talk about the distance of closest approach. What is that exactly?
So think of an alpha particle heading towards the nucleus.
Okay, both positive charges.
Right. They'll repel each other. The distance of closest approach is the point where the alpha particle gets as close as it can before being pushed back.
Like a tiny game of chicken.
Exactly. And we can actually calculate this distance. There's an example in our sources with a proton approaching a gold nucleus.
How close does it get?
Just 23 Fermi.
Fermi? What's a Fermi?
It's a tiny unit of distance. Like, imagine shrinking a meter stick down to the size of the Earth.
Okay, I'm imagining it.
1 Fermi would be about the size of a marble on that scale.
Wow, that's incredibly tiny. So the nucleus is really, really small compared to the whole atom.
It is. And then there's another concept, impact parameter.
Impact parameter, huh? What's that all about?
Imagine you're playing darts.
Okay, I like darts.
The impact parameter is like the distance between your dart's path and the center of the board.
So closer to the center, smaller impact parameter.
Exactly. In the gold foil experiment, a smaller impact parameter means the alpha particle comes closer to the nucleus and gets deflected more.
So that explains why some particles went straight through and others bounced back, right?
Yes. The ones that got closer to the nucleus were deflected more. But even with all these discoveries, Rutherford's model wasn't perfect.
Oh. What were the problems?
Well, for one, it couldn't explain why electrons in orbit don't just lose energy and spiral into the nucleus.
Right. If they were constantly emitting light, they'd lose energy and crash, wouldn't they?
Exactly. And it also couldn't fully explain those spectral lines, those unique wavelengths of light each element emits.
Right. The fingerprint we talked about earlier.
Yep. Rutherford's model predicted a continuous spectrum, but we observed distinct lines.
So clearly, something was missing.
There was. And that missing piece leads us to Niels Bohr and his model of the atom, but we'll save that for the next part of our deep dive. It's like solving a puzzle, You think you got all the pieces, but then there's always one more thing that doesn't quite fit.
Exactly. And with Rutherford's model, one of those pieces was, those pesky spectral lines. Remember, those distinct lines of color we see when we excite an element.
Right. Each element has its own unique set of lines, like a fingerprint. And Rutherford's model just couldn't explain why those lines were so specific.
Okay, so we've got this puzzle and a missing piece.
Yeah.
Enter Niels Bohr. He came along and kind of shook things up, right?
Oh, absolutely. Bohr's model was revolutionary. He proposed that electrons in an atom can only exist in certain specific energy levels.
So not just anywhere, like planets orbiting the sun.
Exactly. It's more like, imagine a staircase. You can stand on one step or another, but you can't just hover somewhere in between.
Okay, that's a good way to visualize it. So electrons are confined to these specific energy levels, these steps, if you will.
Exactly. And that's what explains those spectral lines.
Oh, tell me more.
So when an electron jumps from a higher energy level to a lower one, it releases energy as light.
Okay, and the color of that light depends on?
The difference in energy between those two levels, each jump corresponds to a specific color or wavelength of light.
So those distinct spectral lines are actually a map of the electron's jumps between energy levels.
Precisely. It's like each line is a record of a specific energy transition within the atom.
That's pretty amazing. So Bohr, with this quantized energy level idea, he solved a big problem with Rutherford's model.
He did. Remember how we were puzzled about electrons continuously emitting energy and spiraling into the nucleus?
Yeah, if they followed classical physics, they should have crashed.
Well, Bohr said, in these specific energy levels, electrons don't radiate energy.
Whoa. So they just stay in those levels, happy as can be.
Yep. Until they absorb or release energy to jump to a different level, that is. And that brings us to another important concept, the ground state.
Ground state? What's that all about?
It's the lowest energy level an electron can occupy in an atom. It's like the electron's comfy couch, its most stable state.
Okay, makes sense. So when an electron absorbs energy, it can jump up to a higher energy level, right?
Exactly. That's called excitation. It's like the electron gets a boost of energy and moves to a higher step on that staircase we talked about.
And then when it releases that energy, it jumps back down, emitting light in the process.
You got it. And that's what creates those spectral lines. So Bohr's model really tied everything together, the quantized energy levels, the electron jumps, and those beautiful spectral lines.
It's like a symphony of energy and light within the atom.
I like that. But even with all its successes, Bohr's model had its limitations. There were still things it couldn't quite explain.
Like what? Spill the beans.
Well, for one, it only worked really well for hydrogen, the simplest atom. It struggled to explain the behavior of atoms with more electrons.
Ah, so more players in the orchestra, more complex music, harder to decipher.
Exactly. And then there was that pesky wave-particle duality we keep bumping into. Bohr's model treated electrons as particles with definite orbits, but we know from quantum mechanics that they also behave like waves.
Right. That mind-bending concept that something can be both a particle and a wave at the same time. So where does that leave us?
It means we need to dig deeper into the realm of quantum mechanics to really understand those fuzzy, probabilistic electron clouds and how they shape the atom.
Quantum mechanics. Sounds like we're about to enter a whole new level of mind-blowing.
Buckle up, it's going to be a wild ride.
All right, so we've explored those early models of the atom, and we've seen how Bohr's model revolutionized our understanding with those quantized energy levels.
But we also hinted that there's more to the story, right?
Oh yeah, things are about to get really interesting as we delve into the world of quantum mechanics. I have to admit, this stuff can be a bit mind-boggling.
It's definitely a shift in thinking. But it's also incredibly fascinating because it challenges our everyday intuitions about how things work.
Okay, I'm ready for the challenge. Hit me with some quantum weirdness.
Well, one of the key principles in quantum mechanics is the Heisenberg uncertainty principle.
Heisenberg uncertainty principle. Okay, that sounds ominous.
It's not ominous, just a little bit unsettling, maybe. It basically says that we can't know both the position and the momentum of an electron with perfect accuracy at the same time.
Wait, so we can't know exactly where an electron is and where it's going simultaneously?
You got it. It's like trying to pin down a soap bubble. The harder you squeeze to determine its position, the more likely it is to slip away and change its direction.
Okay, yeah, that's a good analogy. So it's not that we just lack the tools to measure these things accurately, but it's a fundamental limit to our knowledge.
Exactly. It's built into the very fabric of reality at the quantum level.
That's pretty mind-blowing. So Bohr's model, with those neat little orbits, doesn't quite capture this fuzziness, does it?
Not really, no. Quantum mechanics tells us that electrons don't follow those well-defined paths. Instead, we have to think in terms of probabilities.
Probabilities. So instead of pinpointing an electron's location, we're talking about the likelihood of finding it in a certain area.
Exactly. It's like saying there's a high chance the electron is somewhere within this cloud-like region, but we can't say for sure exactly where.
So those orbitals we talked about, they're not like planetary orbits, but more like fuzzy zones of probability.
That's a good way to visualize it. And the shape of these orbitals, those probability clouds, is determined by the electron's quantum numbers.
Quantum numbers. Remind me what those are again.
They're basically a set of numbers that describe the properties of an electron, like its energy level, its angular momentum, and the shape of its orbital.
So Bohr's model focused mainly on the energy level, but quantum mechanics adds more layers of complexity with these other quantum numbers.
Exactly, and that allows us to explain things that Bohr's model couldn't, like those elliptical orbits we talked about earlier.
Ah, right. So the shape of the orbital can be more complex than just a simple circle.
It can be. We can have spherical orbitals, dumbbell-shaped orbitals, and even more intricate shapes.
It's like the electron has a whole playground of different shapes it can explore within the atom.
I like that. And these shapes have real-world consequences, influencing how atoms bond with each other and form molecules.
Okay, so we've got these fuzzy orbitals, these probability clouds. What about those spectral lines? Does quantum mechanics have anything to say about those?
It does. Remember, those lines represent transitions between energy levels, and quantum mechanics can explain why some of those transitions are more likely to occur than others.
Ah, right. Some of those lines were much brighter than others, indicating more frequent transitions.
Exactly. And that's because the probability of a transition is related to the overlap between those fuzzy orbitals we talked about.
So the more those orbitals overlap, the higher the chance of an electron jumping between those energy levels.
Precisely. It's like some transitions are superhighways for electrons, while others are more like backroads, less frequently traveled.
That's amazing. So quantum mechanics not only explains those spectral lines, but also provides insights into the likelihood of different electron transitions.
And that's just scratching the surface. Quantum mechanics has revolutionized our understanding of so many areas of science, from chemistry to material science to even cosmology.
Wow. So it's not just some abstract theory, it has real-world applications that impact our lives.
Absolutely. It's behind technologies like lasers, transistors, and even medical imaging techniques like MRI.
It's incredible to think how this seemingly bizarre and counterintuitive theory has led to so many advancements.
It's a testament to the power of human curiosity and our drive to understand the universe, even when it challenges our deepest intuitions.
Well, I have to say, my mind is officially blown. We've come a long way on this deep dive into the atom, exploring those early models, the revolutionary ideas of Bohr, and the strange and fascinating world of quantum mechanics.
It's been quite a journey, hasn't it? And it highlights how science is a constantly evolving process, with new discoveries and insights always pushing us forward.
And who knows what amazing breakthroughs await us as we continue to explore the atom and its secrets.
That's the beauty of science. It's an ongoing adventure of discovery. And to our listeners, we encourage you to keep that sense of wonder alive, stay curious, and never stop exploring the vast and intricate universe both within and around us.
Thanks for joining us on this deep dive into the atom. We'll catch you next time for another adventure into the world of knowledge.